Hello and welcome to the second part of the lecture in electric motors in the course Advanced Machine Elements. My name is Per Marklund. First part was about DC motors, and this second part I will talk about AC motors and also a little bit about simulations of electric motors. So, AC motors then. For those of you who saw the first part, you can see that I have the same motor here as I had for the brushless DC motor, and that's basically because it is the same type of motor. First we talk about the synchronous motors, and that's actually the same as a brushless motor. Here the stator has windings which are offset in phase. As I said in the first part, you see that you have 3 connecting wires, which means that this is a 3-phase motor. The magnetic field rotates with the synchronous RPM, and this means that the motor is forced to follow the frequency of the current that powers the motor. The rotor here is a magnet, permanent magnet, which strives to be in line with the magnetic field of the stator. The motor rotates with this synchronous RPM, and a synchronous motor cannot start directly from, let's say, the power grid. The rotor cannot keep up with the magnetic field, and it will just bounce back and forth, and it won't start to rotate. What you do with the DC motor, the brushless motors, that you have the speed controller that adjusts the frequency so it allows it to start, and then it just continues to rotate faster and faster. If we move to asynchronous motors, we have normally a cage rotor, which is basically short circuit. This is the most common type of 3-phase or 2-phase motor used in industry. Here you can see a typical industrial asynchronous motor. 1-phase motors with the start capacitor is actually a 2-phase motor with the windings phase shifted a little more than 90 degrees between each other. So you sort of fool the engine so it can be run on only 1 phase, even if it is a 2-phase motor. The characteristics of the asynchronous motors are given here. Same scale as I earlier showed in section 1 for DC motors, where you have the rotational speed going from 0 to 1, where 1 is then the maximum rotational speed, and torque from 0 to 1, where 1 is the maximum torque. As you can see here, the start torque of this motor is, in this case, roughly 60% of the maximum torque. And this is important to know if you are using this motor in a machine that you are designing, because even if the torque is given for the specific motor, you have to be sure that it has enough torque when it starts up, especially if you have a system that needs a high torque in the beginning of the motion. The maximum torque is about 0.8. 80% of the maximum RPM. And after that the torque is decreasing a lot until its maximum RPM. This means that the power output torque multiplied with the rotational speed looks like this. Also it has the maximum power output, roughly about 80% of the maximum RPM. Okay, moving on to simulations of electric motors. And I tried to divide this into two different cases. One case is if you're really interested in the dynamics of the motor. For instance, startup sequence. If you have large variations in RPM and they vary very fast between different RPMs. Here you have important parameters to take into account. For instance, resistance, inductance, or what's normally called back EMF, electromotive force. This often leads to very complicated models. So it's quite difficult to do a really detailed simulation of an electric motor. However, a simple DC brush motor is also quite simple to model. And you can follow this link to see an example on how to model this DC motor. And you don't have to write this link down. What you can do is, if you go to YouTube, just simply write model DC motor in the search field. And this one, modeling a DC motor in Simulink, part 1 of 4. You can follow that and do your own Simulink model of a simple DC motor. And I recommend that you actually do that. But now I will continue with the presentation. Sometimes you don't have to simulate very complicated things. You can instead just use, for instance, what I showed earlier. This, you have the torque versus speed and the power behavior of a specific motor, and that might be enough to use it in a machine. So that depends on what you're looking for with your simulation model. The simulations you will do when you follow the instructions in YouTube is like this. You will model this simple system. You have a brush motor, you have a battery, you have a flywheel, and you will have different input data that will control how this motor works. You have the resistance, which will reduce the current. You have the inductance, which is sort of a resistance towards changing current due to coils. You have a lot of coils in all the windings in the motor. And you have what's called back EMF, counteracting voltage due to changing magnetic fields. And you can model the motor with doing this simple setup. When I follow the instructions, this turn out. But here you have the governing equations, where you have the resistance, the back EMF, and the inductance. And the results, which we should focus on, will be a startup sequence of this motor. So you will see how much current that will go into the motor when you start it up. And this is something you should think about because the startup sequence, or if you have a machine that is going very slowly, then you will have this high current and normally no cooling because the fan is connected to the shaft of the motor, and that might give you problems with the windings and the brushes. So follow the instructions on YouTube and let's move on to frequency drives. Frequency drives is something you need to control the AC motors and also the brushless DC motor. They are used to control the RPM for AC motors. Normally it converts 50 Hz to the frequency of your choice. It can convert one phase to three phase, and therefore it eliminates the need for mechanical RPM control like variators. It can also enable soft start of the motor, and it can save a lot of energy. So we have some power with 50 Hz that goes through the frequency converter or frequency drive, and it ends up with the frequency of your choice. Inside the frequency drive, it consists of three parts. It's a rectifier that converts AC to DC, or in the case with the brushless DC motor, you already have DC, so you don't have to care about this step. You have the mid part, in which you adjust the current. You have a frequency controller that converts DC to AC with a variable frequency. There are some disadvantages with frequency drives. It might give you a noisy outlet voltage, and therefore it can interfere with other systems or condition monitoring systems. And it also gives you more risk for overload and overheating. If you use the frequency drive to power the motor in very slow rotational speed, you might lose the cooling effect of the fan. And that's not the case if you have a mechanical transmission instead to reduce the RPM on the output shaft, because then the motor instead will have a higher RPM. And I would like to end this presentation with talking about two special cases. One is linear motors, and it's basically the same principle as a normal motor, but it's linear arranged as shown here below. You have this stator and you sort of take a pair of scissors, cut it and just spread it like this, and you do the same with the rotor, and then it will be a force instead of a torque. This can be used to have linear actuators in different machines, or for instance more high-tech maglev trains that are hovering above the surface on a magnetic field. In other machines, step motors might be very useful. It's called a step motor because it rotates in step. It's quite simple to control. You use digital pulses. The problem with the step motor is that it has no feedback system normally, and therefore it can lose its position if it's overloaded. Then it can just rotate and it stucks in another position. And you can say that the motor really do not know where it is, but it knows exactly the number of steps it took to go there. And this is something you should keep in mind.